guess I should play a segment from that 1970s classic of the old LP comedy that Cheech and Chong used to do. There was one skit where there's some teacher and all the kids are talking, getting louder and louder, saying, "Class, class." Well, I hope I don't have to do that. Anyway, my name's Glenn LeDrew. Some of you know me. Some of you may not. I moved here to Ottawa back in '92, and off and on had some involvement with the Ottawa Centre RESC, chaired the meetings for a while, and kind of played around doing my own thing. I kind of started off with a very tiny little toy telescope. When I kind of accidentally discovered Saturn one time, I was hooked, back when I was 13 on a cold February evening, 1975. And over that time, gradually, as I could afford it, I got larger telescopes, nothing too huge. But then after a while, I sort of did a bit of a U-turn. The aperture fever bug sort of left me fairly quickly, and it was because I began to develop more of an appreciation of the large-scale sky, the bigger structures that surround us, because we live in a fairly interesting and relatively active galaxy. And looking with bigger telescopes with tiny fields of view tended to restrict you to seeing the trees and not so much the forest. And by concentrating on just looking at targets, those little individual objects, and the stars were basically just a field of little hopping off points to allow you to jump to this interesting nebula or that galaxy or cluster, I didn't feel quite fulfilled. I wanted to understand the home galaxy we lived in. So I ended up kind of retreating quite a lot. And for now the last 20 years or so, I've been doing almost all of my observing with just binoculars. Anything from little small 2.3 power opera glasses, of course the naked eye as well, you can't overlook that. There's certain phenomena that the naked eye beats any optical instrument for. And from those little opera glasses up to binoculars, the biggest I've used myself were about 100 millimeter. And that's pretty good, using two eyes with two 4-inch telescopes. That gives you pretty good depth of penetration, and with smaller instruments you can back off and see things in context. And I began to get interested particularly in dark nebulae, the dark dusty molecular clouds. That's the stuff that stars are made of, including us, along with the planets and such. And part of all of that, beginning to understand the process of the stellar recycling engine of the galaxy, where stars are formed from these gas clouds, live through their lives, expire, sometimes violently as supernovae, other times more gently as planetary nebulae, and the galaxy becoming seeded more and more over time with all kinds of this dirty, obscuring dust. And that's what I find that gives the Milky Way its interesting character, is all these dust clouds. If it weren't for those, the Milky Way would be really very boringly smooth. So all these little dark structures, they're something that sometimes are challenging, and in some cases are actually pretty easy to see if you're in a dark sky. And associated with these dark clouds, very often, are nebulae, both emission types and reflection, depending on whether the gas is excited enough to fluoresce like a neon sign, or just merely reflect the light of nearby stars if the stars don't excite them with their emitting ultraviolet light. And then from these gas clouds we see star clusters, sometimes quite spectacular, with thousands of members, sometimes very subtle with just a handful. And even on larger scales in the star clusters are the unbound groupings of stars that we call OB associations. There are other associations as well, intrinsically interesting, but not observationally so much, because they contain pretty much just the dim stars, more like our sun. And beyond any fairly small distance, they kind of fade into invisibility unless you're using fairly sophisticated equipment or imaging to ferret them out. But the OB associations, they're neat because the brighter stars that comprise those, you can see across a considerable distance of our galaxy because they're so bright. So how do I advance here?
Just do a left click.
Okay. So here's just a wide-angle photo that I just pulled off the web. I chose it because it's very illustrative of a number of the things that I've just been discussing in brief. We see many dark clouds superimposed against the glow of the Milky Way. Of interest in particular is this nice structure here called the galactic dark horse. So large that you can't even get it in the field of view of most binoculars. So it would be almost folly to try to look at that and get the bigger picture with any size telescope. In fact, the binocular will just kind of take in about this much, let's say, with the hind quarter of the horse and one of his legs here. And here's his nose up near the globular cluster M9. One little foreleg here as he's prancing upward across the sky. But here we can see a number of fairly bright bluish stars, and including the yellow, orange Antares. As we know, most stars that make up constellations, they're just chance alignments. They generally lie at very different distances. They make interesting patterns because we just see them projected in 2 dimensions on the sphere of the sky. But in a few cases, there are actually constellations that are, to a fairly good extent, made up of stars that are actually physically related. And one such constellation is Scorpius. As I pointed out, there's Antares, and Cygna, and Tau Scorpii, Rho Ophiuchi, a very much photographed object amongst deep sky imagers. And then the 3 claws of the scorpion here, plus some other stars. You can see some yellowish reflection nebulosity surrounding Antares, a couple patches of subtle reddish emission nebulae, bluish reflection nebulae. In very deep images, this whole area is just shot through with all kinds of dark and reflection nebulae. But all these stars, they were all formed at about the same time from the same general cloud of molecular material that has since dispersed. So we see now the remnants of some of these clouds as these little streamers that are being blown away like windsocks by the stellar winds from these stars. This is a fairly nearby group, about 475 light years away, which is why it's so prominent in the sky. It's a very good example of one of the better OB associations that you can look at with no optical equipment at all. But a binocular really helps to bring out the subtle colors of the stars, and under a very dark sky, you can see some of these streamers of dark nebulosity wending away from the core of this group. Now, in order to understand what's going on in our own galaxy, it helps to study other galaxies that seem to be fairly similar to our own, those being the spiral galaxies. Here's a Hubble photo of M83, a galaxy that's nicely placed for viewing right now, down in the tail end of Hydra. And what it illustrates here is a feature common to a great many spiral galaxies. We, of course, see the fairly prominent arcing spiral arms, delineated by lots of knots of bluish colored stars and clusters of stars and clouds of glowing hydrogen emitting fairly dominantly in the red. But one thing we find very often as well is a concentration of the dark clouds along one edge of these spiral arms. We see it in this arm here in the lower part of the picture, and in the top portion, part of the arm is visible here, where we can see again this fairly organized dark, dusty clouds along one edge of the spiral arm. As we now understand things from the density wave theory, the density wave pattern rotates around the galaxy at a certain speed, but it's slower over most of the inner part of the galaxy than the actual motions of the stars and the clouds of gas. So we end up with this nice curving spiral arm pattern that is turning at, let's say, roughly half the speed of the stars and gas that is passing through the spiral pattern. And because it's a density wave where there's a local enhancement in the gravitational potential, all the material tends to kind of pile up and get denser there. And that's why we see the concentration of the dark clouds. They stand out more prominently because they generally crowd together. And when these clouds crash together like that, that can offset lots of new star formation. And then what we see is emerging from these clouds, continuing on, are all kinds of new, very brilliant stars, the brightest of them, of course, being the bluish O and B type stars, very hot, and which also excite and illuminate a lot of the leftover hydrogen gas surrounding them as the gas is basically being blown to tatters by the stellar winds and supernova blasts from all these newly formed massive stars. And as we track the material farther, the very brilliant blue stars, they die out comparatively quickly in cosmological time, and that's why they tend to fade out to a great extent any distance from the spiral arm, and we tend to find generally dimmer stars. And then as this material continues around into the next spiral arm or spiral arm segment, the whole process starts over again. Various clouds of gas then just collide in the next spiral arm trough, and the process is repeated. And that way a spiral galaxy can remain as a structure like that with new stars forming in an ongoing way over billions of years, even though the stars themselves might only live for a few million or a few tens of millions of years, those bright ones. But there's this recycling going on and on. And the star formation is not particularly efficient either. It's estimated that only about 10% of the material in these big molecular clouds that form lots of stars actually make stars. About 90% is left over, and the stellar winds and supernova blasts tear all these clouds to bits, and then they eventually in other parts collide, coalesce, and then make new stars. In the close-up image in the upper left, it's just a somewhat more high contrast representation of this same section of the spiral arm here. We probably don't have enough resolution to see particularly well, but you can see here's a very good example where there's quite a bright knot in the center with dark and reddish nebulosity surrounding that. This is a kind of a bubble where we'll have probably several star clusters, some other associations that are unbound, and the combined stellar winds are quite vigorously blowing out fairly large, rather transparent and clear bubbles of very hot gas. And it's in these sorts of locations where OB associations tend to form.
Glenn, why is the dark opaque dust localized along the trailing edge of the arms? Do we know?
There is evidence that some spiral galaxies actually have leading arms that don't trail, but they seem to be something of a rarity. The great majority, we seem to find where the pattern is trailing away, kind of in the way that seems to make common sense, like a kind of a lawn sprinkler spinning around, and the way the streams of water would form these arcing structures. That's kind of how it happens. So I'm not sure exactly why. There's matters of dynamics that I don't really fully grasp, lacking the math, that has to do with reflected energy of the density wave pattern just traveling across the galaxy, reflecting from these density troughs in the gravitational potential. It's all pretty complex, and I don't know if I want to strain my brain too much trying to understand it. You're getting the wrong button. Here's another interesting wide-angle photo, probably a mosaic, and it covers a pretty big patch of sky. If anyone can recognize this, I'd have to say you're fairly conversant with your deep sky structures.
California up to the top right?
That's right, California.
Something.
Yeah, Semaeus 147, a supernova remnant, a comparatively youngish one. There's the Pleiades.
Large scale.
And the Flaming Star Nebula here. You'll hear a little bit more about that later. So yeah, so here's the bottom two main stars of Auriga. This is the horns of the bull right here. So the Hyades would be out of the photo down below the screen, roughly the center there. So we can see in a very deep image that the whole area here is shot through with all kinds of very intricately detailed dark clouds. And we can see as well that the general light of the galaxy is actually resulting in the edges of these clouds scattering and reflecting light as very, very, very faint reflection nebulae. And where the cores are denser, we can see them standing out in silhouette as dark, sometimes very irregular and ragged concentrations. So space, even though it's quite empty, it certainly does have a certain fullness to it as well when we look at it in totality. And images like this really help to drive home how much material is out there yet waiting to form new stars. I guess before I forget, I should point out a little interesting back-of-the-envelope experiment, well, not an experiment, a calculation that I did about a quarter century ago, trying to understand just how empty space is. Imagine if you could take, of the estimated 100 billion galaxies that we know of in the observable universe, and assume that each one of them contains 100 billion stars. On average, these stars would be much like our sun. Some are bigger, a great many are a lot smaller. So to say on average about like our sun would be not far from the mark. Now imagine if you could take those 100 billion stars in 100 billion galaxies, that's 10 to the 22 stars, and if you could collect them together like a big sack of marbles, and not, of course, make a monster black hole of stupendous proportions, the volume occupied by that sack of stars would be surprisingly tiny. For instance, in our part of the galaxy, the average separation between any two stars is about 7 light years. So you could say that each star in our part of the galaxy has its own little bubble of space around it, about 7 light years in diameter. Well, all these 10 to the 22 stars, collected like a sack of marbles, would about fit within a mere little 7 light year bubble like that. All those stars in the universe. So that just shows how incredibly densely compacted the material that makes up stars is, yet we can just see the effect visually in the combined light of so many galaxies, you know, each individually just shining so brightly. But there's one way to appreciate just how empty space is, by considering the volume occupied by stars is next to nothing. There we go again. So here's just a simple schematic that would appear in textbooks back in the 70s. I chose it anyway because it simply gets along the point that I'm trying to make here. And this is the process whereby a cloud of gas makes stars, but in a sort of an ongoing fashion, generally. If the cloud is big enough, if you get stars forming in one portion of it, their stellar winds will blow away and disperse the gas, but that can propagate through the cloud as a series of shocks which can further compress the material and make new stars. So if we look back in time, we see here just a representation of an older star cluster that formed some time ago. It has since dispersed all the gas around it. And then more recently, a less old cluster formed. It's also cleared its area from its stellar winds. And then here would be what we could say now is the current moment, where we have yet another cluster forming in a remaining portion of the cloud. It's blowing out a bubble that will fairly quickly break out and then disrupt the material. The shocks that it causes in the remaining cloud will cause yet another rash of stars to form in parts. And that can proceed on through a cloud until the cloud is basically from one end to the other gradually disrupted. And as I said earlier, turning about 10% of its mass into stars, the other 90% remaining yet to coalesce and such with other clouds and make yet more stars. Here's an image, of course, we are all intimately familiar with, the famous Pillars of Creation in the Eagle Nebula, M16. This is a very nice illustration of what happens very soon after a group of stars forms, where the stellar winds of the stars then sculpt the remaining dusty clouds of gas. The denser portions of the gas remain intact for a longer time and tend to become elongated into what are called elephant trunks. These fairly straight pillars here, this long, what looks kind of like a dragon's head feature in here, you'll find in cases like this, these clouds, and even a little tiny tadpole of one here that's almost been completely disrupted, just the denser core remaining, they all point toward the general scene of the crime, where all these stellar winds are blowing outward and fairly rapidly evacuating a large cavity. And then over time, all these surrounding molecular cloud material, it may reveal a few more stars forming inside these areas, for instance, but that will then in turn get disrupted and spread out into space. This might be another familiar image. It's a near-infrared image in close-up of the famous horsehead. So we're partly seeing through the thinner portions of this dusty gas, unlike purely optical images where it's largely almost fully opaque in most of these areas. Here in the thinner parts, we have a little bit of near-infrared light that's able to pass right through, and we can see beyond. And just another example of the sculpting that is occurring. Straight above this picture, some distance away, is the multiple star Sigma Orionis, which is responsible, that system, for causing this to become eroded. The stellar winds are blowing downward, and this denser part is remaining intact for longer, and we have bits of less dense material streaming away at a faster rate. Now here's a fairly important diagram for budding astrophysicists. I'm not going to dwell on it in any length. The main points I just want to get across here is the humongous range of density as well as temperature that is found amongst the interstellar medium. The very dark, dense molecular cloud cores right out into the very hot bubbles of very thin gas that surrounds supernova explosions. So in this diagram, temperature increases vertically from 1 degree Kelvin through 10, 100, 1,000, 10,000, 100,000, a million, 10 million degrees Kelvin. So we can see it's a logarithmic scale. Every step is a factor of 10. And then the density, also logarithmic. 0 being 1 atom per cubic centimeter. There's 100, 10,000, a million, 100 million atoms per cubic centimeter. This dashed line, it shows a directly inversely linear relationship of proportionality, where temperature is inversely proportional to density. The hotter, the less dense in general. But there are exceptions to that, because in the interstellar environment, there's a lot of sources of pressure that can push clouds together and keep them from expanding. And that can cause anomalously high density for their temperature. You know, we can look at some of the molecular clouds, the real dark cores that you can't see through optically because they're so thickly polluted with all this dust due to their high density. You can find very, very dense cores and tiny clumps of very high density that are just being compressed together by the surrounding weight of the gas as the clouds are collapsing to make stars. So you can have incredibly high densities compared to where the gas is more free and is able to be in equilibrium with its surroundings of less dense gas. And the next main class of gas are the kind of ionized clouds, hydrogen predominantly, plus other atoms and ions glowing like neon signs. And then the less dense is what's called the coronal gas, with temperatures of 1 million degrees or so. We tend to find that around supernova explosions as fairly rapidly expanding bubbles that blow out even into the halo of our galaxy because of the sheer energy involved in their expansion. So that's the main takeaway from that. It's just the huge range that we find in the density in the interstellar medium. In fact, when you look at a photo like the previous one of the Horsehead Nebula, you can think of it this way. If we imagine the gas immediately surrounding the Horsehead, the transparent gas we can easily see through, as being kind of equivalent to the air that we're breathing, most of the denser cloud, you could liken that to something like water, 1,000 times denser. And then the denser cores inside would be like lead or even denser still. That would kind of give you a qualitative feel for the range and density. Now, I said if we said the gas just immediately surrounding these dark clouds is kind of like air, well then around the very active areas where supernova explosions occur, or you've got lots of hot stars with strong stellar winds that make very hot gas, that stuff would be kind of equivalent to, let's say, air right up at the edge of space. Just to put it into that scale of things from near vacuum to denser than lead. That's the kind of range of density we're talking about in most of what we're looking at in photographs that show lots of these dark clouds and glowing emission nebulas and clear bubbles of gas. This is a a sort of a special kind of a Hertzsprung-Russell diagram. Anyone who's done any studying of basic stellar astronomy will know what an HR diagram or Hertzsprung-Russell diagram is. It's simply a plot of a star's position on a graph that has luminosity, or its brightness on the vertical axis, and its temperature, or spectral type, or its actual observed color, which to a certain extent are all interchangeable, on the horizontal axis. Now, this data was acquired by the Hipparcos satellite, and it's a very, what's the word I'm trying to find? It's like a kind of a very biased sample. It's only looking at stars within a certain range of brightness, down to maybe about 11th magnitude. So it's not getting a complete census because it's not able to see faint enough to get a good sampling of all the very dim stars, the very faint red dwarfs, which fade into invisibility fairly nearby. So what we get here is a false impression of the B and A and F stars as being very, very numerous, yet the K and M type stars, the little cooler dim ones, they seem to be almost hardly there at all in any numbers. In reality, the situation's reversed. These stars are not as nearly common as the lower part of the main sequence, where the numbers would be huge compared to here. This little bit of a clump here and bit of an extension, that's the red giant branch, where stars spend about 10% of their time quietly burning helium in their cores instead of hydrogen. And just certain stars of a mass kind of similar to our sun, maybe a few times heavier than the sun. Those are the stars that will be the red giants. Just another illustration that kind of puts the kinds of stars in a little better context here. It's very schematic, it's not realistic. It doesn't show the actual size of these types of stars comparatively well, but these sloping lines here indicate the actual radius or diameter of the star in powers of 10. 1/1000th the size of the sun, 1/100th, a tenth. There's the size of the sun, and it intersects right here where the sun is. 10 solar diameters, 100, 1,000 solar diameters. Some stars even exceed that. Some stars are several thousand times the size of the sun. Now, don't let that give you a false impression of them being terribly heavy. They're so big only because they're so bloated. They're mostly a very good vacuum with an incredibly tiny little denser core where all the action's happening with the thermonuclear fusion. So the area that we're concerned with our OB associations is in the upper left corner of the HR diagram, and incidentally right across the whole top where we find all these supergiants, because it's the supergiants that evolve from these bright stars up at the upper end of the main sequence where we find the hot O and B type stars. This little diagram, it also indicates with little tick marks some key points that show how long stars in those positions of the diagram actually live. Like around here we see a lifetime of 10 million years, 100 million, a billion, 10 billion. Have we got that right? Yeah, 10 billion, and then 100 billion. And the very dimmest stars, they can have lifetimes that are into the trillions of years. The very most massive stars, they live but a few million years before they expire. Now the mass range of the stars, an easy way to put things into perspective is something that I kind of invented, if you will, many years ago. I call it the rule of eights, and it goes as follows. The very smallest stars that can viably be called a star have a mass about 8% that of our sun. So that's 0.08 solar masses, and that's right down at the very bottom of the main sequence where the dimmest red dwarfs reside. So that's 0.08. The next number, 1 decade higher or 10 times more, would be 0.8 solar masses, a little bit less than the mass of the sun. Such a star has a lifetime that equals the age of the current universe, about 14 billion years, shall we say. The next key number after that on our little scale of eights is 8 solar masses. Where would that be? Right about here. An 8 solar mass star defines the kind of cutoff between whether a star, when it ends, if it will expire gently as a planetary nebula or detonate as a supernova. And then after that 8 solar mass key fiducial, the last one is around 80 solar masses, which is about the heaviest a star can be that we will ever find. Maybe some might get a little heavier than that, but it's a pretty dicey situation because so much energy is being released in the core of the star that even before it can settle down to any stable core burning, that energy tends to just disrupt the star. So there's an upper limit to how heavy a star can be before it just tears itself apart. So there's my rule of 8s, 0.08, 0.8, 8, 80. Did I forget a number in there? Anyway, so that, a little bit of a framework that you can use then to just build upon to understand the range of masses of stars. But even though the range of mass is not huge, the difference in the length of time they live is monstrously huge. The big heavy stars, they burn their fuel at a prodigious rate. They live fast and they die young. And that makes things interesting in the galaxy because we have all these supernovae going off. And that stirs up the interstellar medium and keeps things mixed up. Actually, here's another little thing you can imagine as well, just to put the process of supernova explosions into perspective. Imagine making a time-lapse movie such that it takes 1 hour for the sun to do one orbit around the galaxy. That would still be a pretty slow, boring movie to watch, waiting 60 minutes for the sun to do one circuit. But during that time, in our little hyperspeed movie, supernovae will be blasting off all throughout the galaxy at a rate of about 30 per second. So it'll be like, just like noisy static almost, with all these detonations while the sun just leisurely cruises around over the period of 1 hour. So that'll give an idea of just how important supernovae are. Here's another kind of diagram that's fairly fundamental in textbooks for budding astrophysicists. And this is just a series of what are called isochrones. They're just lines of equal time, if you will. They show where we will find a group of stars in the HR diagram that were all born at the same time and have the same age. We see the main sequence represented. What we find is that if we have star clusters and we plot these groups of stars in the HR diagram, we will find that the very young clusters will occupy the upper part of the graph, and then progressively older and older clusters will turn away from the main sequence lower and lower and lower down. And the very ancient clusters, they have a turn off right about the point where our sun is right now. Our sun here is near +5 absolute magnitude, and some of the oldest clusters are about, like open clusters anyway, are about the age of our sun. But then the older globular star clusters are older still. Another interesting thing to keep in mind in these diagrams is this feature called the Hertzsprung gap. It was so named because in early plots of stars, there was always this paucity of stars to be found in this area of the diagram. We'd find all kinds of them around the main sequence and in the turn-off region, but then for some reason there would be hardly any here, and then we would find higher concentrations around the red giant branches and where the red supergiants reside. The reason why this gap exists is because as stars evolve away from the main sequence and move over toward the red giant or red supergiant phase, they pass through this region of their development very quickly. They don't spend much time in the HR diagram there. And this is also where we find the kind of variables that we call Cepheids. The Cepheids are in the upper part of the Hertzsprung gap, and then the RR Lyrae variable stars that we find in old clusters like globulars and so on, they're found in the Hertzsprung gap lower down in the fainter regime. But that's an extremely important fact because, as we all know, the Cepheid variables are one of the standard candles that allowed us to build a ladder upon which to construct a model of our universe and discern just how far away things were, especially the remote galaxies. Here's just a little animated diagram I found, very simple GIF that shows, in a very crude simulation, just the way a group of stars, as it evolves and gets older, we find the hot stars disappear from the scene first, become red supergiants and giants, and over time, they just peel away, lower and lower down on the main sequence. So when we plot in the HR diagram a group of stars that we suspect or know to be a cluster, the form of their arrangement here and where that turnoff occurs gives us a very, very good clue as to how old that group of stars is. This is a very important tool in dating groups of stars. Well, I guess I can point out lastly as well, is you'll notice that as the evolution proceeds, we'll start finding a whole bunch of stars here. This is the realm of the white dwarfs. Fairly hot, but not bright. So bluish, hot, and dim. Kind of similar, if you will, to fainter, like K-type stars, or red dwarfs as well. Now the next series of images I'm using here for illustrative purposes, they were taken from a 3D visualization package called Particle Viewer, and it's been adapted with databases. Anyone could use this and make their own database of all kinds of things. It doesn't have to be restricted to this. So it's got a database of all kinds of stars and clusters and nebulae and so on, plotted in actual 3D space to the best estimates of distance as we knew them at the time the data were compiled. So here's a view of kind of looking down on our own galaxy. The center of the galaxy and its elliptical bulge is represented here. The spiral arm pattern is very roughly what we believe our own spiral galaxy pattern to look like. Here, for instance, would be the Sagittarius spiral arm. Here we are in the center of this little grid, which I'll explain shortly, in our own little local Cygnus Orion arm. And then the next arm out is the Perseus spiral arm. This circle wrapping around the galaxy is called the solar circle. It's just a circle of a fixed radius that equals the distance of our sun from the galactic center. It's a kind of a useful number for studies of the galaxy, but we don't need to concern ourselves with that here. What I'm showing here, again, let's forget that grid for the moment. These little colored circles are OB associations, most of the ones that we know. I've colored them such that the purple ones are ones which we believe or know to be out in the Perseus arm. The green ones are the ones in our own local arm, although the ones here that have that bluish color, I've given them that color because they're the ones associated with what we call the Gould belt. A little more about that later. And then the yellow associations are the ones scattered along the Sagittarius spiral arm. Here we've now just dropped our viewpoint down so that we're looking exactly in the plane of the galaxy, looking toward the galactic center with the sun between us and the galactic center. We can see that these OB associations are fairly tightly confined to the galactic plane. There's a little bit of variation in their distance above and below, but for the most part they tend to hug the galactic plane. And that makes sense because that's where we find the disk of the dense molecular clouds that the stars form from on an ongoing basis. Because of the way they collide, they tend to settle down into a fairly thin disk, much in the way Saturn's rings have settled down into a thin disk surrounding that planet. The Gould belt now that we see here, which I just plotted as a very simple grid schematically, we can see it's tilted at 18 degrees. The part in the lower portion here is the closer side to us, and there's the farther side, higher up above the galactic equator. And we'll see that in other representations to follow. The Gould belt, just by chance, we happen to be not far from the center of this system of ongoing star formation expanding away in an elliptical shell. It's getting stretched into an ellipse because of the shearing forces of the differential rotation of the galaxy, and it's expanding outward in little bouts and episodes of star formation, and we'll explore some of those little groups of recently formed stars very shortly. Now here is just a view looking straight down onto our solar system and the disk of the galaxy, and I just showed this view to indicate just how elliptical the Gould belt system has become. Initially it started off as a much more compact structure, But as the stellar winds and so on, supernova blasts that have propagated through the clouds, we're just kind of getting this flat, tilted shell of new star formation advancing out from there. And it first started probably something about 60 million years ago, which actually is about the time the Pleiades star cluster formed, and the Pleiades happens to be fairly close to the center of this structure. And I'm just looking in closer here with a bit of a tilted perspective. The center of the Milky Way is kind of way down, but we're looking at the galaxy at a bit of an angle as we look outward and downward at, let's say, roughly 45 degrees. This little plus symbol, that locates where our sun is. So all these bluish colored circles that schematically indicate the Gould Belt OB associations, you can see they don't very nicely map to a really smooth ellipse. I just put that in there schematically, showing the roughly 2,000 by 3,000 light year extent. But the actual edge and so on, it's not as well defined as that. It's going to be irregularity. I guess I can just point out the center of the system, right about here, the Pleiades star cluster would be, let's see, Perseus 3, probably somewhere about here. The Hyades would be over about here. Remember earlier, right, when my first slide I was showing Scorpius, the claws of the scorpion, and Antares in that region? Well, that's all in this group right here. And there are other related associations with that as well. It arcs across a considerable distance across the sky because it's comparatively close to us, closer than 500 light years. The famous Orion OB association, that's down here almost in the opposite direction, on the other far side of the Gould Belt system. We have different subgroups of different age as well. The older subgroup of Orion is closer to us. The more recently formed ones, well, they're farther out just because the way the star formation progress has expanded out as an expanding shock front. So here is a wide-angle view looking toward the central Milky Way. The center of the galaxy is right here at 0 degrees longitude, 0 degrees latitude. That's the galactic equator. The Milky Way, of course, straddles the galactic equator pretty closely. There's Antares, Upper Scorpius, as it's called. The constellation Lupus, Centaurus, the Southern Cross. You can see that, especially with Lupus, so many of the stars that delineate that constellation have actually belong to this central part of the what's called the Scorpio-Centaurus association. This one here is Upper Scorpius. The center one is Upper Centaurus Lupus, and this part here is Lower Centaurus Crux. And altogether, this group stretches a good 70 degrees across the sky. And if you ever have the good fortune to go down into the southern hemisphere, or at least down into the tropics or near the equator, at a time of year when this area is well placed highest in the south, it stands out so strongly, you just can't miss it. Even though I'm only plotting those stars in the association and I'm not plotting any others, when you look at this in the sky, it's like a signpost that says, look at me. It's just this really nice group of bright stars running at an angle. And when you continue on down, they run down through Vela, Carina, and then down below the Milky Way plain through Orion. And that whole stretch is just right there. And in fact, William Herschel first noticed that on one of his trips to Cape of Good Hope, I think it was. It called attention to him that this stratum of stars that arced across the sky in this tilted band with respect to the Milky Way was so prominent. And this is just the same view, except I've overlaid on the some hydrogen alpha imagery, some fairly deep imagery that shows the very, very dim emissions of hydrogen gas. The brighter areas are just burnt out, quite bright white, like the Eta Carina Nebula here, for instance, or the Running Chicken Nebula right here. But we can see that around Upper Scorpius, we've got some emission nebulosity around, I forget now which is sigma and which is tau. but both of them have emission nebulae, nebulosity, one of them more so. This star here, the center one in the claw, it isn't plotted as a member of the group from the data that I extracted this from, because it has a somewhat discordant radial velocity because of a binary companion, but it is almost certainly a member, and it has a very dim nebula around it. And then around this whole area, there's even a larger shell, almost certainly the result of a supernova blast that sent off the star that is causing this nebula, which we will examine presently. So here we just shifted along a little bit now so that we're concentrating on Upper Scorpius. And here again is that very dim H-alpha shell, very likely the leftover of a supernova explosion. And this star here, which is not shown, that's Zeta Ophiuchi, a fairly obvious naked eye star, surrounded by a huge nebula about 7 degrees across, but exceedingly dim, although almost any imager under a reasonably dark sky can capture images of that quite easily. Well, this star, Zeta Ophiuchi, that's actually a runaway star. It was ejected out of the Upper Scorpius Association something like 1 million years ago. It was a companion around a more massive star. That other star exploded as a supernova, but they were in a fairly close orbit, and the orbital velocity of the two objects was what resulted in their flying apart at a fair speed. The former heavy star that exploded as a supernova, it's flying away at a very high speed, well outside this view, off over here somewhere in Aquila, whereas this star, still relatively heavy, flying at a more sedate velocity comparatively, has only drifted this far away from the group in about 1 million years. And you'll see other examples as well of other runaway stars that are hot enough to ionize the gas around them, and as they travel through space, basically you could think of them almost like train headlights in fog. They're just illuminating the space around them as they go through the interstellar medium. So this star, as it continues on, it will have its own little nebula surrounding it, always a fresh new material it encounters as it plows through the ISM. That's interstellar medium, sorry. Got to be careful about using acronyms. And now here's just an even wider angle view of that same scene. And what I'm showing here is an interesting phenomenon. The center of the Milky Way is right here, and we know, of course, the Sagittarius star cloud here is optically pretty bright. We see the Milky Way quite nicely here. But we see part of the great rift of dust. And if we continue that on, it would go on up into Cygnus, up to near Deneb. But you notice how this material, it sort of diverges up, away from the Milky Way. And here, somewhat more distant clouds, but still not too far away, they also tend to diverge up. We're seeing the effects of a disruption in those local clouds because of, in part, this stellar association that is just blowing everything apart and tearing the clouds up and peeling them away and causing them to drift away in interesting directions. So now we've gone a little bit further around the sky here because there aren't very many optically interesting OB associations. You know, as we go up through Aquila and Sagitta, Vulpecula, Cygnus, things are, or those groups that we find there are fairly far away. They're okay for telescopic observing in some cases, but for you know, the more nearby interesting ones that you can see with minimal aid, there's not so much to see, which is why I passed by that swath of sky. So here is where Deneb would be. This is the wings of Cygnus. Here we've got Cepheus, Lacerta, Andromeda. The Andromeda galaxy is just out of the view down here, and Cassiopeia. So we're highlighting 3 nearby associations here, all related to that Gould belt. And you can see the angle of the Gould belt running this way. Passes right through what's called Cepheus 2. And that includes an interesting star I think some of you will have seen, the red supergiant star Mu Cephei. And very near it is a large dim nebula that contains one of the famous elephant trunk dark nebula features that many amateur imagers like to chase after. Nebula, IC 1396. And that star, they're all related to this Cepheus 2 association. It's about 2,000 light years away. out about around the, or maybe right at the very edge of the Gould Belt. Here's another classical association, and this one is neat because it's now far away enough from all the brighter background glow of the Milky Way that just with your naked eye, when you look at Lacerta and this area, you will readily see in a reasonably dark sky an enhancement in the number of stars here. And that's just because of this actual relatively recent stellar association. And here's a surprising, very recent discovery from 1998 or 99 that resulted just from the examination of the Hipparcos satellite data. The star Delta Cephei, the prototypical Cepheid variable star, is actually a member of this group, as well as, I'm trying to remember if that's Zeta, I believe it's Zeta, or Xi, Cephei, and plus a number of other dimmer stars. They're all fairly nearby. It's nearer than these other two associations. This is now called Cepheus OB6. And as I say, it was only discovered by studying the motions of these stars from the Hipparcos data back in 98, 99. So who would have thought that Delta Cephei would become a part of an association? And again, the same field, just with the hydrogen alpha emission nebulosity shown. Parts of this data are at very low resolution, which is why it looks so terribly blurred. But there's that IC 1396 nebula that has that famous elephant trunk feature that many astroimagers go after right in here. And there's also a shell of emission around here that's a result of a bubble blowout from this group of stars inside whose stellar winds are pushing the gas away and clearing up the space around them. Just for interest's sake, this here is the North American Nebula. And here's an interesting little nebula, very little known, but any amateur imager can capture this. In fact, the brightest part of that I've barely seen with a 100 millimeter bino and a high contrast nebula filter. Very difficult to see. But this, you'll notice that it has a kind of an elliptical ring shape. It's actually a shell. Right in the center of it is another one of our runaway stars, 68 Cygni. It's believed to have been ejected from Cepheus 2, or possibly Cepheus 1, if I remember correctly. One of those two, it's not certain. But it's flying away, traveling southward on the sky. North is up this way toward the upper left. And as it's traveling through space, it's lighting up the gas around it, and even has blown out a little clear bubble around it and formed this ring shell of emission surrounding it. For those of you who like to keep things cataloged, that's Sharpless 2-119. That's that object right there. Now, in the Lacerta association, the only star there that is hot enough to excite any gas is this star right here, 10 Lacertae. It's an O9 type star, which is kind of just barely hot enough to generate enough ultraviolet to light up the hydrogen gas. And we see this interesting shape, almost like a Gumby to me. Sharpless 2-27. Another object that's not too difficult to image from moderately dark skies. We go back to a bit of a wider angle view here, and we're showing several associations in one go here. The main one that we're highlighting is a very large dispersed group called Cassiopeia Taurus, because the stars are spread over a big area of sky between Cassiopeia and Taurus. This is a fairly old group, and it actually is fairly near the center of the Gould Belt and is believed to be among the first generation of stars that formed inside the Gould Belt about 50 million years ago or so. And related to the Cassiopeia-Taurus association, inside of it, as a denser structure, is the Perseus III group. But we'll see that in a little more detail shortly. I could point out as well here, the constellation Lacerta is just outside our view, about over here. But it has a runaway star that it has ejected as well, and it's flying down right now near the Andromeda galaxy of the sky, the naked eye star New Andromedae, the brightest star that's very close to the galaxy that we often use as a hopping off point to find the galaxy. So there's yet another runaway star from a nearby OB association. So now we've Zoomed in here to two of the nearby Perseus associations. Perseus 3, also known as the Alpha Persei cluster, because its brightest luminary is Alpha Persei. It's a fairly subtle Cepheid type variable that doesn't vary very much in brightness. It's probably kind of in the edge of the instability strip that the Hertzsprung gap runs through. And this star, it just might have enough mass to result in its ending as a supernova explosion, probably in the not too distant future. All the other stars, though, they are of lower mass, and they will not explode as supernovae. They will expire more gently. Also in Perseus is Perseus 2, a little farther away from us, right about along the outer edge of the Gould belt. Perseus 3 is somewhat inside, a bit closer to the center. So this group here is famous because of the California Nebula right beside it. And it's being lit up by this star, Xi Persei. And this star, even though it doesn't look like it because it's still very close to its siblings, it's a runaway. But it's actually flying almost directly away from us. And it's some distance in the background and then lighting up by chance some of the gas that it's passing through as the California Nebula. I can point out in passing as well another Perseus association here, but it's very far away. The double cluster is the core of the Perseus 1 group, about 6,000 or so light years away out in the Perseus arm. Nice object for Ridgefield telescopes or big binoculars. The cluster, of course, stands out, but what's very nice about this one is that among the association stars are a half dozen very nice colorful red supergiants that show up in any moderate or large aperture very nicely. And those are all stars near the end of their lives that in the not too distant future are going to detonate as supernovae. Recall our little 1 hour time-lapse movie with supernovae popping off at 30 times per second. Our galaxy is a pretty busy place. And just the same view with the hydrogen alpha imagery overlaid. Most of it, again, a very low resolution, but there's our California Nebula, lurking somewhat in the background behind Perseus 2. By the way, that would be where the Pleiades is. I'm not plotting stars there. This is just the little bit of fuzzy blur of the underlying optical photograph that represents the Milky Way here in this data set. We go back now to a really nice wide-angle view, and we see a fascinating structure. I mean, what catches your eye, of course, is the really bright, glowing nebulae. But look at this very large bubble with some interesting denser portions, like little sheets that we're seeing kind of edge on. Well, this is called the Orion Eridanus bubble, and that's a result of at least one, more likely several supernova explosions that would have happened all as part of the Orion OB association formation. And all these expanding winds are just blowing out a low-density cavity of very hot gas, and where the shock front strikes the general interstellar medium, it causes this low-intensity hydrogen alpha emission of the formerly neutral hydrogen to now be shocked into glowing. And just to give it some scale, this grid here, in all these images, it's 10 degrees by 10 degrees in galactic longitude and galactic latitude. So we can see it's covering 1, 2, 3, 4, 50 degrees easily. So now we just kind of go into the optical view of the Orion OB association, called Orion OB1, but there are several subgroups here of different age. The older subgroup, which is nearer to us, somewhat in the foreground, is subscript A, and then the B is the belt stars and the other neat bunch of stars that surround it as Colinder 70. Subgroup C is the Sword of Orion, and subgroup D is the Trapezium cluster in Orion Nebula. These are all different stages in the process of the ongoing star formation as the previous stars have shocked the gas behind, forming new stars to keep forming, and that will be going on for some time to come because there's a lot of dark molecular gas in behind here, still a bit further on. So there's more stars to be made yet. So here we now see the famous Barnard's Loop, the result of a fairly more recent supernova explosion, as well as the combined stellar winds of so many of these very hot stars. The Orion Eridanus bubble is just too big to take in here. It's covering well more than this field of view. At the head of Orion, there's a young cluster, fairly sparse here, but it's surrounded by a faint nebula, sometimes called the jellyfish. I often see an alien head with an eye, and his little mouth right here, and his pointy chin. Anyway, this is the Lambda Orionis cloud, with the star Lambda Orionis and its cluster around the center. Two more of the nearby associations out along the edge of the Gould Belt. Again, the Gould Belt is running at an angle here, 18 degrees tilt with respect to the galactic equator, which is running up here down the midplane of our Milky Way. And this you can recognize as Canis Major, or Canis Major. This blob, that's just the blurred image of Sirius in this Milky Way mosaic underlying image. It's not a part of this association. It's a very, very nearby star, completely unrelated to any of these OB groups. But Delta, Canis Majoris, and Omicron, these are the two more prominent members of the Calinder 121 association, so named because Calinder 121 is a sparse cluster surrounding Omicron, Canis Majoris. We have a couple of associations here at pretty much the same distance, slightly different age. The Vela 1 group surrounding Lambda Velorum, and then the sparser Trumpler 10 group, just a little bit above it, about in the plane of the Milky Way. And again, we overlay on some hydrogen alpha imagery, and we can see that the Vela 1 association is pretty much in the heart of a huge emission nebula called the Gum Nebula. And this one has got enough brightness in most of its parts to be fairly easily photographed without too much difficulty. I'm not quite sure about the provenance of this nebulosity roughly around Delta Canis Majoris. Most likely associated, but it's something that I haven't really looked into in any detail. Parenthetically, here is the Seagull Nebula around the Canis Major 1 association, but it's quite a bit farther away than any of these structures. It's about 2,000–3,000 light years away. And now we just kind of pull back and we get the Gum Nebula in its entirety, an object that covers 40 to 50 degrees of sky. And it's about, let's say, 1,200 light years away, thereabouts, almost as far away as the Orion Nebula. And it's a result, again, of supernova blasts and stellar winds as well. So when you look at other galaxy photos and see all of these kinds of blown out bubbles with bright blue stars and clusters inside, well, we're seeing right here in our own very galaxy the same structures, but just so close that they cover great big volumes or areas on the sky. And that covers that. It's a pretty quick précis. I'm sure there's going to be a lot of things that you might not remember in detail, but I hope that at the very least it inspires you to look at the sky maybe with a little bit of a wider perspective and maybe investigate looking at things more, especially from a dark site, with even just your eyes, and a little bit of study perhaps beforehand, just to refresh yourself on some of these groups, and mark them on a star map, just circle them out or something, and get out and see what they actually look like, and train a binocular and see them in a little bit more depth. And if the sky is very nice and dark, examine some of those dark nebulae as well, because that's all the material that's just waiting in the wings to make yet more stars and planets and people. Any questions?
Yeah, this is an absolutely fascinating perspective on stuff that we actually look at, except that, as you say, we look inside as opposed to pulling back and looking at the whole picture. It's striking how a number of the OB associations that you've shown us are ballpark, very, really loose ballpark, about the same kind of size, covering the same kind of amount of sky.
Yeah.
Does this mean that the ones that we can see with this perspective are all relatively of the similar age?
Yeah, they're not all that different.
Presumably young because they're not dispersed
Yeah.
fully. So does this mean that if we could actually map this out, there would be a series of size classes, if you will, which of areas of the sky covered by older and older and older similar associations?
Yes, because what happens is that these groups of stars, they're not gravitationally bound like a cluster. So they have a certain internal velocity dispersion. They gradually expand and disperse. And as they do so, covering more and more volume, over time, the differential rotation of the galaxy tends to shear them out, and they spread along, and they then become gradually these fairly long tubular-like things, becoming ever more dispersed. The more massive stars leave the scene. The fainter ones, they remain just to circle around the galaxy for a long time because they live so long. And that's really how all the general field stars that are not really involved in any of these groups came to be. They were formerly members of clusters and associations, and over time the whole scene gets so mixed up. But if you could look, and I'm sure the Gaia data from the ESA is going to give a lot of insight into this, but we were going to find all kinds of these formerly unknown streams of stars that are all related, all kinds of them that we're right in the middle of. There'll be all kinds of streams having their own kinematics, their own particular orbit around the galaxy, and we're just within them, or they're nearby. And then you consider the entirety of the galaxy, and the whole halo is just shot through with all kinds of these former families of stars that have now just become ever more dispersed to make up what we consider the general field.
I was just going to mention earlier that the Gaia HR diagram.
Yes.
Have you seen that one? So I was wondering if you want to include it in there. 'Cause it's
Oh,
pretty,
yeah, I haven't, but
it's pretty astonishing to see. I'm
Yep.
not an expert by any means, but in comparison to the ones
to the
that are on there,
Hipparcos, yeah.
that the definition, especially on that lower.
Oh,
end,
yeah,
is,
they'll get so many of the red
Yeah.
dwarfs now and really flesh that in, yeah. Yeah, I just wanted to show that because what's good about that Hipparcos HR diagram is that it's very useful in showing to us, because we're not looking to very faint magnitudes. When we look with our telescopes or binoculars, we're looking to 10th, 11th magnitude. Much fainter than that in the stars, they might as well hardly be there. So the way we see the sky, it is a very biased representation because we're not sampling it well enough to catch all those huge numbers of exceedingly dim little things that disappear from our. They very quickly go beyond our visibility horizon at very short distances of just maybe 50, 100 light years, and they're fading into just dim specks.
And if I can just comment too, as someone relatively new to astronomy, and I'm wondering how long I can keep using trying that mine out, I've been focused, as you point out, on objects. So this is my first time really getting the chance to step back. I have been a little bit familiar, like for example Bernard's Loop, which I had just stumbled upon about a year ago and realized I haven't actually seen it or imaged it. But it was the first time like stepping out beyond that and realizing that that's just a smaller part of the larger.
Mm-hmm.
Yeah. So and the other thing that caught my imagination is I'd known it intellectually before, but hadn't really appreciated the visual dynamics, as I saw here, of how a supernova triggers star creation. I mean, well, I'd heard that before, and I could have probably pulled that thought out if someone had asked me on it. Here, I now see, you can see with your eyes, you can see when you overlay the hydrogen, you can see that clearly. Yeah. This is a result of that. One triggers the other, and it's just like a popcorn going off. Essentially.
Yeah, space, it's like Swiss cheese. It's just full of all these holes, and then dense clumps, and shock fronts just plowing in from all directions, pushing against clouds and causing density instabilities, and then collapse and new stars forming. Yeah, it's almost chaotic.
For at least one person,
yeah,
to understand that.
What was the name of that software again that showed all 3D?
Actually, you can
images
find
and
that if you just search for Digital Universe by the Hayden Planetarium or Museum of Natural History. AMNH, yeah, AMNH, American Museum of Natural History, Digital Universe. And you can get it in two basic flavors, or at least the last time I checked several years ago. One concerns mostly our Milky Way data, and there's another you can get that has all kinds of external galaxies, so you can study the distribution of galaxies in clusters and so on out to some distance. So that's the software there, but I'm sure there's even more sophisticated packages out now. This one is neat. If you're a real tech head and you like to get into the engine and understand how things work and play around, you can do so much with this because with just simple text files, you can create your own data sets. And I did a lot of that for this. In fact, the OB Association data set that showed those colored circles, it wasn't present before. So very soon after I got it, I said, this will not stand. So I just created the thing, and then I proffered it to the guys that released it and said, yeah, good. And they incorporated it in the next release. So yeah, it's very easy to do. So, you know, for tinkerers that like to play around with software and visualization and all that, it's fairly easy to use when you get into playing around and understanding it. But initially it can seem daunting. And its control interface as well is not very polished or sophisticated. It's not like a usual, you know, Windows-based GUI. It's got, you know, a bit of command line stuff with a bit of clicky kind of stuff, but it comes with a manual and you can mush your way through. But it's very neat because with a graphics card that handles OpenGL graphics nicely, beautiful, nice, smooth animations, you can just pan around, zoom, fly in and out, you know, just see all these things and look at them from different angles. And when you see all that kind of motion, changing the tilt and, you know, azimuth and zooming in and out, the 3D just really then pops for you in a way like you can't see in these static stills. Yeah.
When an astronomer says the word dust, what
Yeah.
exactly do they mean? How big are these things?
Think of it as being much like cigarette smoke particles.
Yeah.
It's of similar size.
And what are they made of?
Two basic flavors, carbon-based, silicon-based. And it just depends on the material. You see, all this dust, what it is, think of it as basically like the effluvia from very unclean burning furnaces, just pumping all this smoky crud into space. And the biggest polluters are the red giant stars, evolving red giants, because as they swell and cool, as they expand, they have much weaker surface gravity, and that means that gas can leave the surface at an even faster rate. So they shed mass at quite a rate. And because they're cool, the gas doesn't have to get very far away from the star before it begins to condense and then form all these little soot-like grains, and then they kind of stick together, and then all that stuff just pollutes space and, you know, makes it hard to see stuff when it collects in sufficient density.
How do the grains form out of gas?
I'm not a chemist, and I wouldn't be able to describe in any detail, but just like in the same way when you, when you combust in an engine and you see this, you know, what seems to be fairly clear gas, and then shortly after, as it cools, lots of smoke particles condense out. So,
There's a simple way of looking at it. Think of scotch.
Drink?
Yeah,
your libation of choice?
one of them, but remember it's distilled. And how you distill it, you produce this vapor, and then you get this vapor to run through a whole series of tubes where it cools, and it then condenses. And a fundamental aspect of chemistry is to actually separate materials out from a gas by getting them to, actually taking the material in the first place, turning it into a gas, and then getting the gas to condense at different temperatures. So now do this in space. You've got this big still, it's called space, and you've got this big cloud, and the clouds can start cold, they can warm up. As they warm up, they can again cool down. Stars generate this material, of course, through nucleosynthesis. But out of a gas, you'll get different elements will condense at different temperatures. Now, obviously, the major element in the gas itself is hydrogen, and it's not going to condense into anything solid, nor is helium. But as you start coming down, lithium, then gradually we start talking about things like oxygen and carbon and nitrogen. And these things will separate out. They then meet each other, silicon. they start meeting silicon. Silicon meets oxygen. And it says, okay, fine, I'm going to combine with you. You've heard of quartz. Well, quartz is basically silicon and 2 oxygens. But if you then bring a little bit of iron along, or a little bit of magnesium along, and that combines in there as well, now all of a sudden you've got a silicate, a rock-forming mineral. And so you start thinking about meteorites. You see them, they come down, they land on Earth. Some of them are very carbonaceous. That's very similar to some of the stuff you're going to see around these black clouds. And other stuff is full of this silicate. But those silicate grains, they're actually condensing out in open space. They could be doing it at the scale of the galaxy. More likely they're going to do it in a disk around a star. Now, there's all kinds of ways this happens, but it all comes down to condensation out of a hot gas.
So as the gas cools, you get the grains from it. Is that the basic idea?
Well, this is one of the really interesting things, is that you start with the idea of the gas, and then theoretically grains should form. Well, those grains are tiny. They're absolutely tiny. They're nano grains. And then the idea is, well, maybe they'll turn into dust. And dust that actually collects together in fluffy balls. You know, the kind of thing you find under your bed, literally. That's the picture that physicists, astrophysicists will project to you. Then there's a problem. They've now got to get from these fluffy balls of dust to grains of what you and I would call sand. Because from grains of sand, the idea is you're now going to build up something bigger, which might be as big as your fist, it might be as big as the Earth. One of the big problems is that these grains don't actually stick to each other. They bounce off each other. So to get from the gases and the dust that Glenn is telling us about this evening, up to something where we can say, well, hang on, I can conceive of dust because I can see it, touch it, it's gritty or what have you. We don't actually know.
Supernova shocks are probably a mechanism.
That will get some of it, but
Yeah.
then to actually get that dust, those grains, because they're nanograins, they're nanodiamonds we're talking about,
Yeah.
to get them to then stick together and form grains of what we would call dust because we'd sweep it into a dustpan, that actually is physically something that's very, very difficult to do. That's what I was talking about, the RASC at the last meeting.
Well, to appreciate how much dust there is out there, by weight, if you took a sample of average interstellar gas and you took the dust out and weighed it, it would weigh about, I always get this confused, I think it's 1% by mass.
Something in the
I think
order.
it's something of that order, about 1%. Of course, in the early universe, there was none of that stuff before the first stars had a chance to pump all their dirty effluvia into space. So space was quite transparent compared to now. Here's another way to understand just how filthy space is. I mean, 1% by mass, that's considerable. Imagine if you took a big long plunger, about 10,000 light years long, stuck it out into the galaxy, inserted into the far end a plunger, and rammed it home to within about the last 1 meter. You would now have in that last meter of a 10,000 light year pipe gas at about the same density as what we're breathing now. And within that gas, the visibility would be less than a meter. It would be as polluted as the dirtiest house fire.
That's interesting.
You mean polluted as the city I grew up in as a child.
So any other questions, or are we all sort of dazed into a state of insensate incoherence?
No, I do have another question, Glenn. I find it fascinating to listen to this from the point of view, the perspective of an amateur astronomer, and I'm sure that all of you share that. But one of the questions we've been asking ourselves throughout this series is, what are the professionals doing with these objects, these associations in the case we're talking about this evening? What are the professional astrophysicists asking themselves about these associations, or are they?
They are.
What
Well,
are
yeah,
they?
it's a fruitful field of research because it does a lot to inform our understanding of the whole stellar birth and death cycle. Yeah, it's one of the questions that is still being attempted to be answered anyway. Is just how the stars form. The efficiency of the process. you know, how much of this is left over and so on. Understanding the galaxy itself, you know,
In so many-
kinematically, dynamically.
In so many of the questions we've actually examined during this series of talks, the answer to that question has been, yeah, the professionals are looking at it, but there's 5 schools of thought, and there's no consensus. Where do things stand in the science? Are we heading towards a consensus? Are they completely divided between multiple schools of thought?
I don't get the impression that there is a lot of divergence, you know, of any real great magnitude. You know, not quite like, say, Halton Arp and his ideas
Mhm.
compared to the rest of the community that's studying galaxies and so on. You know, that there's more discord there, I think, than there is in the area of piecing together the puzzles of what's going on dynamically in our own galaxy. I mean, I've not done a lot of studying of the professional literature. Certain areas that I'm interested in, I'll delve into. So I'm a bit focused, and I guess I'm not seeing the real big overarching picture. It's a bit hard to do that just you know, by yourself as a hobbyist, I guess. You know, you have almost by nature you'll tend to specialize slightly to some extent.
I think if anything is can disrupt, it's the Gaia data has the potential to disrupt a lot of the standing theories, because it's the sheer volume of data
Oh yeah.
that is bringing in on an exponential scale.
Yeah, just by virtue of the statistics alone. Yeah, compared to the paucity of data we had to deal with until now.
And the ability of even of us to interpret it, the huge volume of data being fired at science essentially, and how do you focus, you know, people to go through the data and pull out the information you need. There's too much data.
Oh, I know. The number of papers that are going to result from this one mission, there'll be in the many thousands.
So at least 2 of the more releases coming in the next, every couple of years, they release more.
Mhm.
Then at the risk of wearing you out, there are so many things that in our own galaxy the professionals have looked at, then they've looked at Andromeda and said, oh, we can actually see either analogues or even the same thing. I was really surprised when I realized that just how much they could see in terms of globular clusters in Andromeda.
Yes.
These are much bigger features. Mind you, they're far more dispersed. Is there any sense that the professionals can actually see these sorts of associations in the Andromeda galaxy?
Oh yeah. Yeah, even in just optical images, they'll reveal themselves as increased densities of these, you know, hot blue stars, for one thing. There'll be a number of instances if you don't have sufficient resolving power, what might look like a really bright star could turn out to be more like a fairly compact, you know, maybe not very populous cluster, else it would be really bright, but you know, you can end up with things that might appear stellar at first glance, but could just be some compact star clusters. But yeah, these associations, they occupy enough volume that they're certainly resolvable, and those intrinsically bright stars now, with the gear we have, it's easy to see those.
And are they similar to the clusters in our
As far
own
as I
galaxy?
know, yeah, they share a lot in common.
Okay.
If our 2 galaxies are about similar age, and have had a not very different history in terms of the star formation processes and so on, you know, we could expect it should have many of the kind of properties that we see here in terms of, you know, the fraction of dust to gas and the star formation efficiency rates, so many ways, yeah. We're 2 siblings, you know, the 2 main galaxies in our own little local group. And as we know, it seems that at some point in the future, destined to merge or collide in some fashion.
I just read an article a little while ago, Andromeda's been downgraded in size a bit. We have, Mercury has more dark matter, so total mass, so now they're more closer to being equals than one bigger than the other. I don't know my source, I can't remember, I read a lot of science stuff and which one that particular was, but because I've been teaching outreach and stuff, that of course it's more massive than we are.
Right.
But that appears to be equalizing according to whatever I've recently.
Yeah, well, the supposition of the amount of dark matter, of course, is contingent on the behavior of the stuff, the baryonic matter we can see, So yeah, if there are indications that the kinematics are such that, you know, it can only be explained by more or less dark matter, yeah, that's how we would infer that. So as long as we keep refining the values of these key datums, you know, like rotational velocity, have a good idea on the distance involved and so on, and, you know, construct a model of the gravitational potential, then all the rest falls into place. Sort of the simplest way I can, you know, answer that issue concerning dark matter anyway. It's just something that we infer so far, no direct evidence at all.
I have a question. How do we identify, or how do scientists identify the members of a OB association?
Well, there are a number of things. The first one obviously is proximity on the sky. That's a first clue. And we're not too likely to find young stars that are very widely separated for the distance and still be kind of related, so you find them fairly close together. And then you take a look at their spectral type and their brightness, and if you take into account as well the extinction by any patchiness in the dust clouds that might dim them and make them seem like they're farther away than they really are, you resolve that by, if you don't get a direct measure of the distance, which now Gaia, of course, is really refining, because we can nail these things down now in our neighborhood so well, it's astounding. But until then, the spectroscopic parallax, so that at least you've got a fair idea of where it is in distance, and then you look at radial velocity, proper motion. With all these now, you can construct the actual space motion. And if the space motion is in fairly good agreement, then that's a fairly strong clue that they are related. Because groups of stars, be they a cluster, fairly tightly bound, or a loose association, they don't tend to have a high velocity dispersion or difference in velocity that tends them to have them spread apart fairly quickly. They tend to very slowly disperse. So as they're orbiting around the galaxy, their own little peculiar velocities with respect to the group is small, and then we'll end up seeing a group of co-moving stars that are a family. They will have just very nice parallel proper motions, or maybe not parallel if we can get perspective. You know, if we see them converging or diverging, if they're not too far from that geometric point on the sky. But anyway, the proper motion is a good clue just by itself, but if we've got actually then the radial velocity and a good estimate of distance, then we can get the full space motion, where we have, you know, those 6 critical datum, you know, the position, distance, radial velocity, proper motion, and so on. So it's all these things together, and the more you have that is supportive, then the more confident you are in your conclusion. So with Hipparcos, that helped advance things fairly significantly. Before that time, our distance estimates were certainly rather poor, but now Gaia, that's a revolutionary leap. So that's just going to open things up. I mean, a lot of the stuff I showed you here, there's going to be a number of these stars that'll say, oh no, they can't belong, the kinematics, distance, that's all wrong. And then there'll be a whole bunch of new ones that'll be added in to flesh it out better. And also lots fainter stars. We'll end up seeing these groups as just, you know, incredible families of thousands of stars in each one, versus maybe, you know, the dozens that you know, we can say with some confidence now.
If you haven't seen the Gaia HR diagram, I've got it on my phone, I'm just searching for it while we're talking here.
Okay.
But I understand we haven't found our own sibling stars. I think science is still looking for the ones that, in
Yeah.
the birth of our sun.
Yeah, it's pretty hard now because we've gone around the galaxy about 20 times since we formed, and that's an awful lot of opportunity for any of our little siblings to have gotten quite perturbed into a different enough orbit that it can throw any doubt on that, because they'll have their own fairly considerable peculiar velocity. It's only when you've got groups that have maybe gone around the galaxy for like half an orbit where you can have still fairly good confidence on common motion as being a good indicator. But you know, much more than that, after an orbit or so, things they start getting stirred up enough individual encounters with stars near dense molecular clouds can then, deflect their orbits, and then the velocity dispersion of that group, it becomes ever more different over time. Then you're kind of left just with the momentum, basically the speed, the energy they have as they orbit the galaxy, or the V velocity vector as it's called. That's kind of becomes almost the last clue. And if you have a fair separation in distance, so many variables. Even trying to look spectroscopically and see if we have similar chemistry, that's no guarantee that we can necessarily find our little sibling either.
But it would be cool to look up and to say.
It would be,
that's
yes.
one of ours, so.
Yeah, but 20 orbits,
Yeah.
that's a lot of stirring up. In fact, it's thought that about 80% of all star clusters, these are gravitationally bound clusters, let me get this right. Just trying to remember the numbers now. Yeah, 80% of clusters are thought to not even survive as a bound group beyond 500 million years. Yeah, that's about right, 500 million years. So that's like 2 orbits around the galaxy. Most clusters don't survive that. So we've got around 20.
So you'd be saying that the associations you've been showing us are probably less than 100 million years.
Oh yeah, most of these are kind of in the range of 5 to, say, maybe 20 million years. And that's just hardly any distance around that clock when you're talking 250 million years to go once around the galaxy at our distance from the galaxy.
Is there a clear definition distinguishing between associations, clusters, and asterisms?
Oh, absolutely. Asterisms are just pure chance line of sight arrangements that have no physical relationship.
Isn't there a big difference considered an asterism?
Nope.
It's
The central 5 stars are actually the core group of the Ursa Major stream, a star cluster that has just recently dissolved.
So it's considered a cluster then?
Oh yeah.
Okay,
Yeah,
I
it's
know
the center.
an asterism.
It's the center of the Ursa Major stream, and these stars, they surround us all around the sky. We're kind of inside this stream of stars of a dispersed cluster, and that core of it is very close to us, only about 75 light years away, which is why we can find ourselves enmeshed within its co-moving stream members, in a volume of space that's a lot larger than the distance of Ursa Major to us. So asterisms, they're just pure unrelated alignments of stars. They might look pretty, but that's about it. Clusters, by definition, they are gravitationally bound. The stars orbit the common center of mass, and an association is too dispersed to be gravitationally bound. It's already in the act of spreading out. They can't be held together by their own mutual gravity. They are now moving under the force of the general gravitational potential of the galaxy. These stars in association, practically, they don't even really see each other. To them, they might as well be in isolation, and they're moving just in this general field produced by this huge galaxy of 200 to 400 billion stars. I guess we're fresh out of questions. Okay, well.
I think one can thank Leonard.
I inspired just one of you to get out there and look at the sky with fresh eyes. It will be mission accomplished.
Well, I think you've inspired more than one of us.